these drivers lost control at very high speeds. The result was tragic for one driver and fortunate for the others. But why? What made the difference between walking away and being carried away? The answer can be found in some of the most basic laws of the physical universe. Hi, my name is Griff Jones. I teach high school physics. And behind me is the Insurance Institute for Highway Safety's Vehicle Research Center. It's a fascinating place where research engineers assess the crash performance of vehicles by running tests, and where they evaluate new technologies to prevent injuries, like this state-of-the-art head protection system. What's exciting for me is that this is a laboratory of practical applications in the subject I teach. And because they're set up here to crash cars and analyze those crashes, this research center provides a perfect venue for illustrating the physical laws that govern the outcome of car crashes. So follow me, and for the next few minutes, I'll take you behind the scenes where we can explore the basic science behind vehicle crashes. Let's learn about car crashes and physics. Why'd this dummy get left behind? It's called inertia, the property of matter that causes it to resist any change in its state of motion. Galileo introduced the concept in the late 1500s, and almost 100 years later, Newton used this idea to formulate his first law of motion, the law of inertia. It's why the dummy fell off the back of the truck. It was at rest, and it wanted to remain at rest. That's inertia. It's the same property that keeps the china on the table as you pull the tablecloth out from under it. Now, what about a body in motion? Am I a body in motion? You bet I am. I'm moving 35 miles per hour. But from one perspective, it may not look like I'm moving at all, because in relationship to the passenger compartment, my position isn't changing. But if you look at me from the outside, you can see that I'm moving at the same speed as the vehicle, in this case, about 35 miles per hour. And if Newton was right, and we know he was, I'm going to keep on moving at the same speed until an external force acts on me. Now, what does this mean to occupants of a moving vehicle? Watch this. See how the car and the crash test dummy are traveling at the same speed? Now watch what happens when the car crashes into the barrier. The front end of the car is crushing and absorbing energy, which slows down the rest of the car. But the dummy inside keeps on moving at its original speed until it strikes the steering wheel and windshield. This is because the dummy is a body in motion traveling at 35 miles per hour and remains traveling 35 miles per hour in the same direction until acted upon by an outside force. In this case, it's the impact with the steering wheel and windshield that applies the force that overcomes the dummy's inertia. Inertia is one reason that seatbelts are so important. Inertia is one reason that you want to be tied to the vehicle during a crash. If you're wearing your seatbelt, you slow down with the occupant compartment as the vehicle's front end does its job of crumpling and absorbing crash forces. Later, we'll talk about how some vehicles' front ends, or crumple zones, do a better job of absorbing crash forces than others. But for now, let's get back to Newton. He explained the relationship between crash forces and inertia in his second law, and the way it's often expressed is F equals ma. The force F is what's needed to move the mass m with the acceleration a. Newton wrote it this way. It's the same thing. Acceleration is the rate at which the velocity changes. But if I multiply each side of the equation by t, I get force times time equals mass times a change in velocity. When Newton described the relationship between force and inertia, he actually spoke in terms of changing momentum with an impulse. What do these terms mean? Momentum is inertia in motion. Newton defined it as the quantity of motion. It's a product of an object's mass, its inertia, and its velocity or speed. Which has more momentum? An 80,000-pound big rig traveling 2 miles per hour? Or a 4,000-pound SUV traveling 40 miles per hour? The answer is they both have the same momentum. Here's the formula. P is for momentum. I don't know why they use P, they just do. equals m is for mass and v is for velocity. P equals mv. That's momentum. And what is it that changes an object's momentum? It's called an impulse. It's the product of force and the time during which the force acts. Impulse equals force times time. Here's my favorite demonstration of impulse. I have two eggs, same mass. I'm going to try to throw each egg with the same velocity. That means they have the same momentum. If the impulses were equal, why do we have such dramatically different results? The wall applies a big stopping force over a short time. The sheet applies a smaller stopping force over a longer time period. My students say the sheet has more give to it. Both stop the egg, both decelerate the egg's momentum to zero, but it takes a smaller force to reduce the egg's momentum over a longer time. In fact, so much smaller that it doesn't even crack the egg shell. Now let's relate this to automobiles. Both of these cars have the same mass, and both are traveling at the same speed, 30 miles per hour. Like the eggs, they have equal momenta. As a result, it will take equal impulses to reduce their momenta to zero. One car will stop by panic braking, and the other by normal braking. If both drivers are belted so they decelerate with their vehicles, the driver of the car on the bottom will experience more force than the driver on top. This is because if the impulses must be equal to decelerate each car's momentum to zero, the driver that stops in less time or distance must experience a larger force and the higher deceleration. A g is a standard unit of acceleration or deceleration. People often refer to g's as forces, but they're not. Fighter pilots can feel as many as 9 g's when accelerating during extreme maneuvers. And astronauts have felt as many as 11. People in serious car crashes experience even higher G's, and this can cause injury. Now consider what happens when a car traveling 30 miles per hour hits a rigid wall, which shortens the stopping time or distance much more than panic braking. Let's again assume the driver is belted and decelerates with the passenger compartment. And let's also assume the car's front end crushes 1 foot with uniform deceleration of the passenger compartment throughout the crash. In this crash, the driver would experience 30 G's. However, if the vehicle's front end was less stiff, so it crushed 2 feet instead of 1, the deceleration would be cut in half to 15 G's. This is because the crush distance, or the time the force is acting on the driver, is doubled. Extending the time of impact is the basis for many of the ideas about keeping people safe in crashes. It's the reason for airbags and crumple zones in the vehicles you drive. It's the reason for crash cushions and breakaway utility poles on our highway. And it's the answer to the question I posed at the beginning of this film. This driver survived the crash because his deceleration from high speed took place over a number of seconds. This driver decelerated in a small fraction of a second and experienced forces that are often unsurvivable. Up to now, we've been looking at single vehicle crashes, but if we look at 2 or more objects colliding, we have to use another one of Newton's laws to explain the result. Even though the first cars wouldn't appear on the roads for over 200 years, collisions were an active topic of physics research in Newton's day. Back in 1662, Newton and his buddies formed one of the first international science clubs. They call it the Royal Society of London for Improving Natural Knowledge. One of the first experiments they did was to test Newton's theories on collisions using a device like this. What do you think is going to happen when I release this ball and it collides with the others? Let's try 2. It's as if something about the collision is remembered or saved. Newton theorized that the total quantity of motion, which he called momentum, doesn't change, it's conserved. This became known as the law of conservation of momentum, and it's one of the cornerstone principles of modern physics. Before we apply this to crashing cars, we need to know something else about momentum. It has a directional property, so we call momentum a vector quantity. This means if identical cars traveling 30 miles per hour collide head-on, their momenta cancel each other. Inside the passenger compartment of each car, the occupants would experience the same decelerations from 30 miles per hour to 0. The dynamics of this crash would be the same as a single vehicle crash into a rigid barrier. What conservation of momentum tells us about collisions of vehicles of different masses has important implications for the occupants of both the heavier and lighter vehicle. In a collision of two cars of unequal mass, the more massive car would drive the passenger compartment of the less massive car backward during the crash, causing a greater speed change in the lighter car than the heavier car. These different speed changes occurred during the same time, so the occupants of the lighter car would experience much higher accelerations, hence much higher forces than the occupant of the heavier car. This is one reason why lighter, smaller cars offer less protection to the occupants than larger, heavier cars. There's a difference between weight and size advantage in car crashes. Size helps you in all kinds of crashes. Weight is primarily an advantage in a crash with another vehicle. Newton was a pretty brilliant guy. The laws of motion he advanced over 300 years ago are still used today to explain the dynamics of modern-day events like car crashes. But even Newton failed to recognize the existence of energy. Even though it's all around us, energy is tough to conceptualize. Scientists have had difficulty defining energy because it exists in so many different forms. It's usually defined as the ability to do work, or as one of my students says, it's the stuff that makes things move. Energy comes in many forms. There's radiant, electrical, chemical, thermal, and nuclear energy. In relating the concept of energy to car crashes, though, we are mostly concerned with motion-related energy, kinetic energy. Moving objects have kinetic energy. A baseball thrown to a batter, a diver heading toward the water, an airplane flying through the sky, a car traveling down the highway, all have kinetic energy. But energy doesn't have to involve motion. An object can have stored energy due to its position or its condition. This is a device that delivers a force to a crash dummy's chest to test the stiffness of the ribs. The force is a result of the kinetic energy being transferred from the pendulum to the dummy's chest. As the pendulum sits at its ready position, its potential energy is equal to its kinetic energy at impact. When it is released and begins traveling towards the dummy's chest, the potential energy transforms into kinetic energy. If we freeze the pendulum halfway, what is its potential versus kinetic energy? They are equal. When has the pendulum reached its maximum kinetic energy? Here, at the bottom of its swing. The amount of kinetic energy an object has depends upon its mass and velocity. The greater the mass, the greater the kinetic energy. The greater the velocity, the greater the kinetic energy. The formula that we use to calculate kinetic energy looks like this. Ke, that's kinetic energy, equals 1/2 mv squared. That's the velocity multiplied by itself. And if you do the math, you'll see why speed is such a critical factor in the outcome of a car collision. The kinetic energy is proportional to the square of the speed. So if we double the speed, we quadruple the amount of energy in a car collision. And energy is the stuff that has potential to do damage. The connection between kinetic energy and force is that in order to reduce a car's kinetic energy, a decelerating force must be applied over a distance. That's work. To shed 4 times as much kinetic energy requires either a decelerating force that's 4 times as great, or 4 times as much crush distance, or a combination of the two. The rapid transfer of kinetic energy is the cause of crash injuries. So managing kinetic energy is what keeping people safe in car crashes is all about. Brian O'Neill is the president of the Insurance Institute for Highway Safety. And identical to that. That's incredible.
So one of the things we do, we put grease paint on the...
He runs the Vehicle Research Center and is one of the foremost experts in the world on vehicle safety.
Where the dummy hits. We use the term crashworthiness to describe the protection a car offers its occupants during a crash. Now, crashworthiness is a complicated concept because it involves many aspects of vehicle design. The structure, the restraint system, it all adds up to this single term we use, crashworthiness. We use the stripped-down body to illustrate the concepts of good and poor structural designs for modern crashworthiness.
Brian, why is it important for the vehicle structure to perform well in a crash?
Well, this is what's left of the body and structure of a car that was in a crash, and we use this to illustrate the point. Basically, we want the occupant compartment or the safety cage to remain intact. We don't want any damage or intrusion into this part of the vehicle during the crash.
Okay.
We want all of the damage of the crash confined to the front end.
So even though all this metal looks the same, it's actually different. The green metal is intended to crumple, to give in the collision.
If we can crumple the front end of the car without allowing any damage to the occupant compartment, then the people inside can be protected against serious injury. Basically, we want the front end to be buckling during the crash so that the occupant compartment is slowed down at a gentler rate.
Right. It's kind of like jumping off of a step and keeping your knees straight and landing on the floor versus bending your knees when you land.
Exactly the same concept. So this is a vehicle that did well because there's very little intrusion anywhere in the occupant compartment. These elements here, even though they're strong enough to hold an engine and suspension, actually buckled and crushed just like they're designed to do. So the damage is confined to the front end. We look at a vehicle like this, and this is an example of a very poor safety cage. This vehicle was in a 40-mile-an-hour crash, and as you can see, that the occupant compartment has collapsed. It's been driven backwards. As a result, the driver's space has been greatly reduced. So someone sitting in this vehicle is obviously at a high risk of injury.
So even if the restraint systems do function properly, the airbag, the seat belts, the person still is in great danger.
This person in this vehicle, even with a belt system and an airbag, is at significant risk of injury because the compartment is collapsing.
So it's analogous to shipping a box of china. You can have all the best packing in the world around the china, but if the box is weak, you're going to break the china.
When the safety cage collapses, you're going to have injuries to the occupants. So this is an example of poor crashworthiness. But this vehicle was in the same crash, 40-mile-an-hour, offset crash, and you can see that now the safety cage has remained intact. There's very little intrusion anywhere. The damage is confined to the crumple zone of the vehicle. This is the way it should be. A person in a crash like this, wearing their seat belt and protected by the airbag, can walk away from the crash with no injury.
Right. If I stand over here and I just look towards the rear of the car and I ignore the airbag, this doesn't even look like it's been in a crash.
That's right. This is good performance, good crashworthiness.
In our shipping box analogy, this is an example of a strong box.
That's right. The people in this box will be protected.
Brian, obviously this car performed well, but what's in the future for crashworthiness?
This is an illustration of how good we can do with frontal crashworthiness, but frontal crashes are only part of the problem. We obviously also have to pay attention to other crash modes, and one of the most important is the side impact crash. Now, this is a vehicle that was in a severe side impact crash. This vehicle was going 20 miles an hour sideways into a pole. And as you can see, in a side crash, you don't have all the crush space you have in a frontal crash. We just have the width of the door and the padding, and in this case, we have an airbag on the inside, which creates even more space. We inflate the airbag to create more crush space. And we also have an inflatable airbag to provide head protection up in this region. This deploys from this roof area here. So the physics are the same, the engineering challenges are greater.
I am always looking for ways to relate the physics that I teach to the real world that my students experience. And nothing is more relevant than traveling in an automobile. You probably do it every day. I hope that makes the message of this film important to each and every one of you. I've always believed that if a person truly understands the laws of physics, that person would never ride in a motor vehicle unbelted. And now that you've had a chance to learn some of the finer points of the physics of car crashes, I hope you agree. I also hope you've learned why some of the choices you make about the type of car you drive and the kind of driving you do can make a difference in whether you survive on the highway. Remember, even the best protected race car drivers don't survive very high-speed crashes. The bottom line is, the dynamics of a motor vehicle crash, what happens to your car and you, is determined by hard science. You can't argue with the laws of physics.